Oh, hello. I'm Jim the Filter Guy, and you're at the Abbey Road Observatory. I'm just wrapping up from doing some thermal imaging for my day job, which is a really good segue into the topic of today's video. Imaging with only infrared light. But before we get into that, why don't you take a sec to click that like button, and if you want to stay up on what the ARO is doing, subscribe to the channel. That'd be great. All right, well, what do you say we get the show on the road? Welcome, everyone, to my talk titled Seeing Beyond the Visible, the Science and Art of Amateur Infrared Imaging. In this talk, I will introduce everyone to the science behind infrared imaging, including a review of the electromagnetic spectrum, the types of sensors used for IR imaging, brands and models of available IR filters, and the performance of your optics when imaging in IR. After that, I will present some of my own personal experiences imaging in only infrared light for targets such as the Moon, galaxies, planets, and emission nebulae. Let's start with a review of the electromagnetic, or EM, spectrum. EM radiation is a form of energy that travels around our universe at the speed of light, in the form of waves, with photons being the subatomic particle that is responsible for the energy exchange with other matter. Depending on how much energy the photons are carrying, the wavelength they propagate at varies, with higher energy being associated with shorter wavelengths. Humans have a very limited ability to detect EM radiation, being able to perceive only the narrow range of wavelengths from 400 to 700 nanometers, what we call the visible spectrum. We have, however, managed to build instruments that allow us to observe light at many other wavelengths, whether they be as long as radio waves or as short as gamma rays. In this talk, we're going to be talking about the part of the EM spectrum just below our perception, infrared. This band has been subdivided into smaller subbands based on their application. Starting just beyond the visual band is near infrared, followed by short wave, mid-wave, and long wave. Beyond long-wave infrared is the far infrared band, which is not of much use here on Earth, as I will explain in a moment. By the way, there are a few common units used when talking about wavelengths of EM radiation. Angstroms, here, 10 to the minus 10 meters, are often used for discussing light wavelengths shorter than the visual band. Nanometers for light in the visual band, and micrometers, or microns for short, throughout the rest of this presentation. Now, you may be wondering why in the subbands that I showed you a moment ago are there holes in the wavelength coverage here and here. The answer has to do with our atmosphere. As light propagates around our planet, it tends to interact with the molecules making up our atmosphere, with some wavelengths of light passing through unaffected, but others getting absorbed by the various constituents like water vapor and carbon dioxide. As a result, there are wavelength windows through which light passes mostly unhindered, with these windows corresponding to the subbands I defined earlier. Note from this graphic that pretty much all light at wavelengths above 14 microns is absorbed by the water vapor in our atmosphere, making observations at these wavelengths impossible from the Earth's surface. This absorption of far-infrared radiation is also the main contributing factor to the greenhouse effect that keeps our planet warm. The limits our atmosphere places on observing in the infrared band explains why all the professional infrared observatories tend to operate either at very high altitudes, where there is much less water vapor, or in outer space, where there is no water at all. While we are talking about infrared observatories, have you ever wondered why scientists even care to see light at such long wavelengths? What is it they are trying to see anyway? Well, a large part of that answer has to do with what the temperature is of the things we are trying to study. Back in 1900, this cheery-looking fellow, German physicist Max Planck, postulated the black body radiation law, which is based upon the supposition that EM energy is emitted only in a quantized form, this quanta later being identified as the photon. Planck was awarded a Nobel Prize in 1918 for his discovery. In Planck's law, the spectrum of the light emitted by an object is related to its temperature. Note from the different blackbody emission curves plotted here how the wavelength of the peak emittance shifts to a progressively shorter wavelength as the object's temperature goes up. A very hot object, like, say, a blue supergiant star, it emits most of its light in the UV part of the spectrum. Our Sun, with a surface temperature of around 5,500 Kelvin, emits most of its light in the visual and near-infrared bands. A cooler red dwarf star emits more in the near and shortwave infrared bands. Coming closer to home, hot metal from, say, an aircraft exhaust, my professional area of interest, emits mostly in the short and midwave bands. An object around room temperature, including everyone watching this video right now, emits light mostly in the long wave infrared band. Finally, objects that are really cold, say, for example, interstellar gas and dust, they have their peak emittance in the far infrared part of the spectrum. Thus, by knowing the temperature of the object we are trying to observe, you can select the best wavelength of light to use for your observation. Conversely, measuring the emission spectrum of an object allows you to remotely determine its temperature. So, now we know how to pick the wavelengths we want to observe. Next, we need to figure out how to do it. Sensors used for infrared are not unlike what is in your phone camera. They are all made from some combination of semiconducting materials. This graph presents the detectivity spectra for just a small number of sensors in use today. There are two main types of infrared sensor. The first is photovoltaic, which give up an electron when a photon hits them. This is how your phone camera sensor works, which happens to be made out of silicon, the blue line shown at the top of the plot. The second sensor type is photoresistive, which have varying resistivity depending on the flux of photons striking them. The sensitivity of these different materials increases when you cool them to very low temperatures. Cooling can be achieved through a number of methods, such as a Peltier thermoelectric device, which can get you to around 250 Kelvin. Dry ice can get you to around 196 Kelvin, and liquid nitrogen to 77 Kelvin. That's minus 196 Celsius, if you were wondering. Liquid nitrogen was the default cooling method up until about 20 years ago, when the Stirling cycle device, sort of a mini refrigerator, was developed that can get you to temperatures comparable to liquid nitrogen. Before we leave this slide, I'd like to direct your attention to the green curve in the upper left. I have included it for interest's sake. It is the detectivity spectrum for the sensor material presently used in Generation 3 night vision goggles. Now that we are familiar with the different types of sensors used to observe infrared light, let's have a look at some examples of the cameras made using those sensors. First is the Generation 3 night vision goggles I mentioned. They use room temperature indium gallium arsenide sensors that can see in the visual, near, and shortwave infrared bands. They are used primarily by the military and sell for around $4,000 to $8,000 US. Next is a long-wave IR camera, the T640, made by U.S. infrared camera giant FLIR. It uses a room temperature microbolometer and sells for around $30,000 US new. This is an example image my coworkers and I captured during a flight test using this camera. Notice how even subtle differences in surface temperature, all in the room temperature neighborhood, are well resolved by the camera. My final example is a short and midwave IR camera made by Canadian company Telops. It uses a Stirling cycle cooled indium antimonide sensor and sells for around $100,000 US. This example image was captured with a version of this camera we use at my work. As you can imagine, because of the cost, we tend to carry it around like a newborn baby. Note in the sample image how the hot helicopter engine and exhaust pipe are well resolved in this waveband, but other cooler details are lost. I'm guessing many of you are now saying to yourself, why the heck are you wasting our time talking about infrared imaging when the cameras cost as much as a luxury automobile? What say we back up for a moment and talk about sensors again? Remember from the sensor material plot I showed earlier the blue curve for silicon that was at the top? Well, it so happens that we can do quite a lot with that particular sensor material, and compared to the other sensors mentioned, it is dirt cheap. Right now, the biggest global producer of commercial camera sensors is Sony in Japan. A big portion of their sensor market is dedicated to security and remote monitoring cameras. These cameras require high resolution, high sensitivity, high dynamic range, and low noise. Lucky for us, these are all sensor traits that astronomers want too. This graph illustrates the spectral sensitivity of some different Sony sensor technologies. 5 to 10 years ago, charged coupled devices, or CCDs, the red curve on this plot, were the preferred sensor for astronomical imaging. Since then, complementary metal oxide semiconductor, or CMOS sensors, have surpassed CCDs with superior readout speed and lower read noise. The fact that CMOS sensors are easier to mass produce than CCDs is one of the main reasons for their rise to dominance. The plot shows the spectral sensitivity for 3 different generations of Sony CMOS sensor. The yellow curve is for older front-side illuminated Exmor sensors. Blue for more recent backside illuminated Starvis sensors, And finally, the green curve is for the most recent generation of improved backside illuminated Starvis 2 sensors. There are a number of different Sony sensor models using the Starvis 2 technology, the most common being the 4 models listed here. Cameras made with these sensors start at around $300 Canadian. I have also included the spectral sensitivity of our dark adapted eye on this plot, in cyan, just to drive home how much more of the electromagnetic spectrum is available to us through the use of these sensors. Now that we have an affordable camera worked out, let's talk about filters. The camera sensors we just looked at can detect UV, visual, and IR, but we only want to observe the infrared band. To accomplish this, we need to add an IR pass filter. Most IR filters out there are absorption type, where the dye that is used in the glass will selectively absorb light in the UV and visual bands but allow IR light through. There are a few filters out there that use not only absorption but also interference type coatings, like those we see used for light pollution filters. But these are generally for more specialized applications, i.e., to create a bandpass filter instead of just a high-pass filter. This graph illustrates the spectral transmissivity of the main IR filter types available today for amateur astronomy. The high-pass filters are most common, with cut-on wavelengths generally at 650, 685, or 850 nanometers. German filter manufacturer Astronomic sells 3 different broad bandpass filters with cut-on wavelengths at 642, 742, and 807 nanometers. The 642 is shown here on the graph in blue. There is also a narrow IR bandpass filter popular for imaging the outer planets called a methane filter. They have their center wavelength located around 889 nanometers, shown in green on this graph. The table shown here summarizes the filters available from the main amateur astronomy OEMs, with prices being reasonable for the most part. If you are looking to get yourself a filter on a shoestring budget or want something out of the ordinary, you can usually find something online through eBay, Amazon, or AliExpress. Be careful with those outlets, though, as quality and finding the correct size can often be a problem. The last technical thing to discuss about infrared imaging is your optics. The telescopes and camera lenses we use as amateurs are not typically designed for observing infrared light. Refractors, including camera lenses, suffer from chromatic aberration, an inability to focus all of the different wavelengths of light to the same focal plane. Apochromatic refractors are better at this than ED doublets, and ED doublets are better than achromats. Generally, reflecting-type telescopes don't suffer from chromatic aberration. However, newer mirrors that use dielectric coatings may or may not work at infrared wavelengths. This image is an example of what you will get if you try to use an achromatic refractor, in this case a traditional camera lens, in conjunction with an IR pass filter. The stars are all bloated and fuzzy, and deep sky objects are blurred. Now let's get to the fun part, actually using IR imaging to enhance our amateur astronomy experience. Imaging in infrared allows us to reduce atmospheric seeing effects, combat light pollution, increase contrast, and reveal details that would otherwise be hidden. Let's have a look at some of my own personal examples. My first example application is for imaging the Moon. One of the main challenges with lunar imaging is how our atmosphere bends the light passing through it, a property that varies with air density and thus temperature. This variation in temperature density over time is called seeing. You can get reports on the seeing quality using sites like Clear Dark Sky or Astrospheric. The useful bit of information for us is the fact that seeing effects are worse at short wavelengths. Thus, by observing using only IR light, we can minimize the effect of seeing on our lunar imaging. As an example, consider these two videos that were captured around the same time on the same night. The video on the left was captured with a blue bandpass filter installed, and the video on the right using an IR bandpass filter. I think we can all agree that the video captured using the IR filter is much steadier and sharper. Not only are seeing effects greatly reduced using the IR filter, but it was also much easier to achieve a good focus. The difference in the quality between the videos is further illustrated with these quality graphs that were generated by AutoStackerd when I processed the videos afterwards. If you look closely at the green line, you can see that there are roughly twice as many frames above 75% quality in the IR video. Note that these graphs plot relative frame quality within each respective video. The graphs do not reflect the fact that on average, the frames captured with the IR filter are much better quality than those captured with the blue filter. This average frame quality difference is apparent when we compare the final stacked and sharpened images. Although the result of stacking the top 10% of 5,000 frames turned out pretty well using the blue filter, the final image captured using the IR filter is significantly sharper, has more contrast, and has more fine details visible. As a final moon example, consider this image captured by me from my backyard back in 2013. It was captured using a UV IR cut filter, before I had learned about the benefits of using an IR pass filter. It was captured on a rare evening of good seeing conditions and represents pretty much the best I was capable of achieving at the time. Compare that to this image captured in 2020 from the same location using the same equipment, but using an Astronomic ProPlanet 642 filter. Seeing on that evening was only average. The IR pass filter is an accessory that can turn average conditions into excellent results. The next example application of IR imaging I have to share is of galaxies. These objects emit light over a broad range of wavelengths, a result of them being made up of a large number and variety of star types. The broad spectrum nature of galaxies makes them difficult to observe from light-polluted locations. Fortunately, man-made light pollution is almost entirely in the visual band, but galaxies emit light well into the infrared band. This presents an opportunity to combine a camera and an IR pass filter to achieve enhanced views of galaxies. To illustrate what I mean, consider this plot that compares, in red, the spectral luminance of an urban night sky, my backyard in central Ottawa, Canada, in fact, compared to that of the galaxy M51 in blue. Note they are plotted against different y-axes. Those of you adept at reading logarithmic plots can see that in the visual band, from 0.4 to 0.7 microns, the sky is about 200 times brighter than the galaxy. However, in the IR band, above 0.7 microns, the sky is only 20 times brighter. Thus, by observing the galaxy in only IR light, we can achieve a large increase in contrast. To further quantify the effect, I have made a prediction of just how much contrast increase we can expect for each of the main IR filter types I described earlier. I have prepared this prediction for the 3 different generations of Sony CMOS sensor, labeled here as 1, 2, 3 for Exmor, Starvis, and Starvis 2 respectively. I have plotted percent contrast increase versus signal-to-noise ratio. An SNR greater than 1 means better than no filter, and less than 1 is worse than no filter. My predictions suggest that contrast increase goes up as the filter cut-on wavelength goes up. However, at some point between 685 and 850 nanometers, adding the IR filter results in an SNR worse than no filter, i.e., to get the same object brightness and noise level in the image, one would have to use a longer total exposure time than with no filter, which really isn't all that desirable. This is, of course, just theoretical. Let's have a look at the effect an IR filter has in practice. Here are 4 images of the galaxy M66 in Leo captured from my urban backyard using 4 different filter configurations. All 4 images represent the same total exposure time of 5 minutes. There is a clear advantage to imaging the galaxy in the IR band, consistent with my predictions. If you look closely, you will notice that the areas showing more contrast with the IR filters are not the bright star-forming regions in the spiral arms of the galaxy, but are instead of the central bar and overall extent of the galaxy. Imaging the galaxy in the near-infrared band is preferentially showing us the cooler stars that exist in the galaxy's halo and other subtle tidal features. Using IR to observe galaxies under light-polluted skies not only enhances their contrast and SNR, but it also allows us to observe objects not otherwise possible. This image of M97, the Owl Nebula in the constellation Ursa Major, was captured from my backyard. Of special interest is the compact galaxy group Hickson 50, circled in the lower left. The galaxies in this group range in brightness from magnitude 18.7 to magnitude 20. Even after a single 20-second exposure, these very faint and distant objects were visible. By using the IR band, I have essentially removed any constraint placed on my observing from my urban backyard. The next IR imaging example I have to share is of planets. As we saw for the Moon, seeing effects are also improved when imaging planets using infrared. Using IR also allows us to make some features easier to see, such as Jupiter's belts and zones, Saturn's rings, moons, and Venus's clouds. Here are some images I captured of Saturn on the same evening using both visible and infrared light. Note how the IR image is much sharper and has better contrast. A similar effect can be observed in these images I took of Jupiter. Seeing was poor that night, but even still, you can see the improvement in sharpness and contrast provided by the IR pass filter. If you carefully compare these side-by-side images, you may note that some features look quite different in the infrared. What we are seeing is differences in the chemical composition of these planets' atmospheres. This is even more apparent in this Jupiter image I captured on a night of better seeing. Note how the great red spot is uncharacteristically bright in the infrared compared to what we are used to seeing in the visual band. The brightness of the GRS signifies an abundance of methane in that feature. The last thing to note on planets is that, although I don't show it here, it is possible to combine the IR image data with the visual band data to produce a composite image of better quality. For example, one can use the IR image for the luminance channel and combine that with the hue and saturation channels from their visual band image to create a sharper, full-color image with more detail. The last amateur application of infrared imaging I have to share is of emission nebulae. Cold dust and gas can block light from stars in the visible band, but not in the infrared. This fact is beautifully illustrated in this famous Pillars of Creation comparison between the Hubble Space Telescope and the James Webb Space Telescope. Note how many more stars there are visible in the JWST image. This is something that we as amateurs are also able to explore. Here is my attempt at imaging M16, the Eagle Nebula. First, invisible light using a multi-narrowband filter, and then using an IR pass filter. The IR pass filter I used still allowed hydrogen alpha emissions through, so much of the emission nebula is still visible. However, it is very apparent that there are many more stars visible in the IR image. I personally find the star cluster associated with the M16 star-forming region to be much more apparent in the IR image. This effect is further demonstrated in my second example. Using the same two filters, I captured images of M8, the Lagoon Nebula. Comparing the visual band image to the IR image again shows a large disparity in the number of stars visible. The size and star count of the cluster associated with M8 is truly only visible in the IR image. It is also much more apparent in the IR image that small, cool stars, which are not visible in the visual band image, are far more numerous than the large hot stars. In summary, IR imaging is easily accessible to amateur astronomers today. The cameras necessary and the filters we require are all readily available at affordable prices. There are a number of different targets that benefit from IR imaging, including the Moon, planets, galaxies, and nebulae. Although I have not explored the application myself, in theory, comets also give off a lot of infrared light, and so should benefit from IR imaging. I have greatly enjoyed exploring the night sky using only infrared light. I encourage you to give it a try. If anyone has a question about infrared imaging, please feel free to leave a comment below. Alternatively, you can contact me by email using the address in my channel description. If you enjoyed this video, please take a moment to click the like button. To stay up to date on everything the ARO is up to, hit the subscribe button below. Until next time.